processor
Mm-hmm.
that's suitable to their specific task. For example, for MacBook, iPad Pro, all of that is more to multimedia for video editing and graphic editing, so that they can use customized or such as M1 processor, the new processor that are powerful enough to handle those tasks.
Yeah.
So I think in the future, iPhone maybe will use M1 if
Mm-hmm.
not possible.
Yeah. Yeah, but M phone is a bit powerful processor, because for their smartphone, they already have their own legacy processor developed by Apple itself lah. So I think is this M1 is we're gonna focus on uh, more bigger thing, right? For example, because normally people that use MacBook, I mean, they're involved in like video editing, something like that, so very heavy, multimedia stuff. So I think they're looking forward into that. So I think that the next step is that they're gonna replace the processor for their Mac desktop, right? So I think that's the direction that they're heading to. Yeah, but yeah, in the end, so you see, right? So what's happening in the market, so whoever can offer, the best product, they're gonna win, right? Yeah, but it's not just a product, and price is also matter lah. So that's why, our discussion in SoC design is a huge topic lah. So it's a huge topic. Then I know it's a very broad to cover, but what we'll try to discuss in our class is a lot of on the surface thing, but the things that I think is important for you guys to know, so that later if you guys go in the industry, at least you can carry this knowledge and help you guys to to survive, right, in the industry. All right. So before I'll go into or the point I left you guys last week, right? So which is contact and via management. So let's go and look into just try to summarize, because I think it's good to summarize things up, so that we'll remember the things, because I don't want we just learn this semester, and all the things gonna fade away as you guys finish the semester or the course, which is I think it's not good. All right. So last week we already covered the physical design, right? So physical design is related to how we manage, right? We manage all the things inside the chip, right? So how we gonna sort the cell, so it's relating into how we connect all those transistor in the chip, right? So how we sort the power, the power line in the chip, so how we optimize it, because in the end, if we fail this physical design part, so maybe we can have high performance product, high performance SoC, but it's terrible in power consumption. No, just imagine you have smartphone, right? And then you use your smartphone, and after 15 minutes your smartphone already starting to heat up. I think, I mean, of course we don't like it, right? So we want our phone to be can maintain enough as we are using it. I mean, it's not like hitting too much and can disturb the convenience of the user. So you see here, I mean, like, that's why to understand how we can optimize the physical design, is very important, so that it will not interfere the quality of the end product that we are intended to design lah. So as you can see, this is a ASIC design flow, which is similar with the SoC design. So the only thing that is maybe the uh, uh, the new thing that need to be involved when we involve the SoC design is design flow, is including the analog circuit, for example, this micro electromechanical circuit, where you want to embed the sensor together with the SoC, or any analog circuit that you want to embed together. So those are the things that will make the difference in the design flow. Apart from that, it's almost going to be the same with this normal ASIC design flow. So again, ASIC is application specific integrated circuit. So this is where the IC that is not reprogrammable. So once you load the or create the circuitry, then you are not able to change it anymore. But it's very efficient, and in terms of power, if you are mass production it, it's going to be very cost effective, right, compared to the programmable solution. Right. So like you can start from design spec, RTL, then synthesize. So here's the physical design. So there are many tools involved, right? So as you can see, Synopsys and Cadence are name of the two company that produce multiple tools for ASIC design flow. As you can see, there are many names of the tools that can be used in different step of in the design flow. Right. So yeah. So here the the file and who produced the file. So we need to understand this so that when we go into the design, we know the limitation. We know that some of the files we can have it from the synthesize team, and then some of the design we need to get it from the vendors, right? And some of the design we need to ask from the foundry. Right, so this is the difference between the RTL code and convert it to netlist, because when you want to make it into circuitry, right, on the in the chip, right, so of course you have to change, right, from the RTL code, the this hardware description language, into netlist code, so that it is more on the circuitry oriented or gates oriented. Right, so this is about floor plan, power plan, and placement. Right, so crop synthesize routing. Right, so all right, these are the I think that the summary of the challenges that we are having in the physical design step in this ASIC design flow. So as you can see, the congestion, regarding the cell density, pin density, signal integrity, crosstalk. So as you are, putting more cells in it, you are putting more circuitry in it. It become dense, right? So when it becomes dense, so one of the things that affected is the signal integrity. So the crosstalk. Do you guys know what is crosstalk, guys? Do you know what is crosstalk? Any of you know? Cha, Q, Yip? Hello, guys.
Not sure.
Not sure lah.
Oh, yeah.
Okay. Alright. Yeah, have
Uh,
you heard of crosstalk before, Q?
oh, no, no.
Okay. What about Cha?
I heard about it before, but I didn't sure for the meaning.
Okay. Alright. So, okay, crosstalk. Last time, I mean, at your house, guys, do you still have the landline phone? The one that's connected to the copper cable one. Who still have that phone? Like 04 for Kedah, for KL,
Oh,
03 number.
the house phone like that.
Still
Uh,
got it.
yes, I still got
Ah,
it.
okay, you still got it. So if you guys, I'm not sure. I don't think you guys use it, right? So maybe some your parents or somebody want to call your parents, they might use it. But what happened, in the early days, so this connection, they're using copper, right? So copper, because copper is one of the best, electrical conductor, right? The best is gold, of course, gold is too expensive to be used. But that's why in semiconductor they use gold, because gold is the best semiconductor, what do you call it, conductor, electrical conductor. So they're using copper. So what happened, because a lot of copper line, right? So when they bundle it up, so sometimes they already put the insulation so that they don't touch each other. But when they put it under the hole, right? So there's a mouse. Sometimes the mouse go and bite it, and then bite the insulator and open up the copper, and then sometimes it's raining, and then there's a water filling up the the cable line. So what happened is that there's a crosstalk happening. So what is crosstalk? When there's a two copper line, they touch each other or they are close to each other. When they carry information, they can get the information from the other line. So that's why sometimes when you talk, then you can hear somebody, but right now you don't really experience it. But sometimes last time, if you using like there's a phone booth, right? That you need to insert coin and then you need to insert card. I'm not sure. I think during your time you're not using it anymore, but during my time, I was using the coin slot phone, to call. And then sometimes you can hear other people talking to each other, right? So why is that happening? So there's a crosstalk. Same thing when it got congested, right, in the processor, in the chip. So what happened? The signal is close to each other, and then crosstalk can happen. So when one line is carrying a signal, this presentation form. Maybe this one here first. Okay, all right. Okay, so let's say there are two lines, right? So and it's close to each other. So here is carrying a signal, right? So 1011, right? So it's carrying the signal to this direction, and then here is carrying another signal in another direction, right? So sometimes these signals can go and interfere the other line, right? So that is what is crosstalk. So these are the challenges in this physical design. So we'll try to get rid of this. And then power, right? So there's a power leakage, and then there's a dynamic power, short circuit power. So there are a lot of things in power consumption. Like today we're going to discuss about the power management. So if you guys see, we talk about this Apple processor, and then Cha bring up about this why Google comes out with their own processor for their Pixel 6 phone. So we can see the trend that power is the main issue in the industry. So if you want to have smartphone, right, you want your smartphone to be able to last for at least one day before you need to charge it, right? When you about to go sleep, right, you need to charge it. So that's fine because you are not using it. But if you have a smartphone, then you have to charge it every 2 or 3 hours. That's kind of annoying, right? So that's why when we talk about power, power is very important. So power then relates to battery, right? So if the processor or the SoC is consuming a lot of power, then you need to have a bigger battery. So that's why if you remember, during the early time, right? So when they first invented this, mobile phone, they have a phone like this, so they call it Arthur phone. Arthur, right? So Arthur, the number is 010, right? So this is the phone that they say, if you throw it to the dog can die. Yeah, so it's very big. And then but you can bring it in the forest, you still can get line. Right? Because why the design is big, right? Because of the battery, because they need to they consume a lot of power, then you need to bring a big bulk battery together with it, right? So power leakage power is very important. For example, the processor in this new this car, right? The electric car, the autonomous car. There are a lot of processing involved. So that's why they need to have a very powerful SoC, but low power consumption. So that's why you see even Tesla, they engage with AMD to work on their SoC processor, to design whatever processing that they need to cater on the Tesla car. Right, then timing. So timing is the thing that we need to be aware of. So why timing is important? Because if you miss any timing, then you're gonna get wrong output. So this is the thing that we don't want to happen. And although in simulation, you already simulate it, right? So everything works fine. So when you insert a signal, then you expect, for example, you insert an input, right? So your input is 1 1, and then you are expecting the output to be 1 0 1, right? So this is your output, right? And then okay, this is what you get from the simulation. But after, the physical design, because of the line is congested, because of the delay, what happened when you insert 1 1, then your output you get 1 1 1, for example, right? So this mean that something wrong with the timing that's happening inside the circuitry, right? So lower technology, temperature inversion, so how you control the temperature, and then the area, right? So this is the main thing, one of the main thing that the company is looking into. For an example, right? So they talk about, the example of this the what is the different, why Apple moved to SoC, right? So they say, like, most of the processor right now is using the x86, right? So x86, so this x86 is being used by AMD, right? AMD and also Intel. So this is architecture, old architecture, not old, but I mean it's the famous architecture that being used before this. But then there's another company, right? So where they call it as ARM, right? So this R stand for RISC, right? So what is RISC? So RISC is reduced instruction set computer. Right, so the instruction is not complex compared to x86. So that's why ARM, the power consumption for ARM is lower. And then the area optimization is lower. Okay, where's the main difference here? So they say that if you look into the video, right, for example, they have a program, right? So when they have instructions, so in case for x86, right, so let's say they have three instructions. So all three instructions, so they have three instructions, all those three instructions will be sent at a time into x86. Then they'll figure out how to manage the instruction. So that means, that there are overload of connections inside the architecture. Sometimes you can still optimize it, but the thing is that this is GPU, right? So this is a general processor, the general processor unit, right? So it's meant to do a lot of processing. It's general, but ARM you can customize it, right? So you can customize it. So at one time it's going to execute one instruction, right? So one instruction at a time, right? So but the circuitry will be simpler, right? And then of course when the circuitry will be simpler, and then the power consumption will be lower, right? So that's why we can see a lot of trends right now is going into this ARM architecture. But even if you look into, this big company, they already been using ARM also. For example, Intel, right, and then AMD, they already have the the ARM architecture inside of one of their products or multiple of their products, right? And then mixed signal design. So when there's mixed signal, digital and analog. So this is another thing, right? The challenge. And then the runtime, right? So this is the whole runtime that will affect the final output, right? So this is basically the things that we have learned in physical design, right? Okay, guys. So anything you guys want to discuss in physical design before we go into our new topic for today? Okay, let's look into this is the last thing, right, that I skipped last week because of the time. Right, so contact and via management. Okay, contact is, if you look into the this transistor design, right, the cell in the physical layout. So all of these transistor, it need to be connected, I mean, of course there's a connection. So that's the contact point. All right, and then the other thing is that via, right? So via, normally if you guys go into the industry, right, so they're gonna have a multiple layer. So they have layer one, and then they have layer two, And of course, there are a lot of circuitry in here. The transistor and everything, right? And then here, the second layer, they have another one, right? So you need to connect, right? So between the first layer, right, the first layer and the second layer. So how you going to connect it? And so this is what they call via, right? So this is the connection between the multiple layers, right? So yeah, one of the things that the challenges in this physical design is contact and via management. So you have to figure out where's the best place and the most optimized place that you want to place this contact and also via in the physical design. So basically that's about this contact and via management. Okay, all right. Okay, anything else you want to ask about physical design before we go into chapter 3?
No, doctor.
Okay, all right. So you guys can follow. Hopefully you guys can follow. If you guys have any problem, just let me know. Okay, all right. So before we start, wait, I guess I need to go and fill up my cup because I need to drink a bit as long as I'm talking. Because a lot of talkings need to be done today. All right. Okay. Let me go and fill up my drink first. Okay, all right, guys. So today we're going to cover about energy management techniques for SoC design. Right. So these are one of the important topics in this subject. So we are covering this chapter for 2 weeks. Right. So this week and next week, and then by end of this class, I'm gonna give you guys some tasks so that you guys can come out in the next class and do some presentation before we start our class, right? And so energy management techniques for LC design. All right, so these are the introduction. As you guys know, right? So reducing the power and energy consumption. So this is has become, the important thing themes in the SoC design. So we talk about, a lot of examples nowadays. People want to have something that is can last longer, right? Your smartphone, your smartwatch, right? So because it's kind of annoying when you need to charge it, a lot of time. Just imagine like you have, a smartwatch and you want to go travel and then all of a sudden, the battery is gone, right? So it's kind of useless. You are wearing the watch, but you cannot see the time. So it's just for fashion only. So that's why when we talk about the SoC, so we talk about reducing the power and energy consumption because this has become, the important things, for the user to pick and choose, to use the technology. Right. So you can see a lot of driving factors that drive, into the SoC design into this direction. Try to reduce power and energy. As we can see, the popularization of portable electronic devices. It has become trends. So people have multiple smartphones. People are using their smartwatch, to track their activities. People upload their activities on the, there's social media, on the Facebook. You're jogging, like for example, you're just jogging 100 meter, and then you upload it. So activities done today, kind of some things that has become trend, right? Then raising demand for reliable and stable computer systems. So people are willing to pay for a good system, right? So that's why you see, right now, you look into the iPhone price, how much, guys? How much is the iPhone price? The new one?
About 4,000.
Yeah, but still, I'm not sure. Maybe some of you even using the iPhone, right? But people are willing to pay, right? So it's if you think again, 4,000, you can buy a motorcycle, and you can buy used car that is drivable. Yeah, not pretty, but you can drive it. So, but if you think that value, people are willing to pay, so that means people are starting to liking it, right? So liking, and people are willing to spend a lot of money into it. So even there's one thing, I'm not sure, I forgot the name. This one cooker, it's an electronic cooker. I think it's from the western side. The price is 7,000. You just imagine, guys. So this is just the I think kind of smart cooking devices. So the price is 7,000, and people are willing to pay for it. So that's why we can see, nowadays, this technology has becoming part of us. Even right now, like yesterday, I was talking with my wife regarding the robot vacuum. Yeah, I'm not sure you guys are aware of it or not. But there's a kind of you can have a robot that's gonna do all the vacuum things for you guys, so you don't have to instruct it. So sometimes they're gonna move around and try to clean your house, which is it's very cool, right? So it's like you don't need to have a man, but you need to prepare like 1,000 or 2,000 ringgit. You need to buy it to make sure that your house is clean. And then the worldwide environmental destruction. Of course, this is one of the another thing, right? So as you are using a lot of batteries, and then you throw the batteries, I mean, all this kind of thing gonna bring harm to the environment. Right. So yeah, of course, the popularity of the portable electronics has becoming the biggest factor that forcing this SoC industry to lower down their power consumption. All right. Okay, and then okay, this is just example. So the typical power consumption for okay, so the typical power consumption for and this electronic product, right? So it's a 10 to 50 watt when employed chips are not optimized for low power. And then assuming a battery yielding around 65 watt hours per kilogram is used, so the terminal would require an acceptable of 6 kilograms of battery for 10 hours operation. So, if there's a product that consume around, this rate of power, so you need to have, 6 kilogram of battery, and it can only last for 10 hours. So if you're using 500 grams of battery, so the terminal can only operate for 1 hour without recharging it. So as you guys can see, so these are the driving factor. You don't want to go and carry a huge and big battery around, because to sustain the life of your electronic products that you are using, right? Alright, so alright, so and then the second need for low power comes for strong pressure for designers to have high-end products to reduce their temperature. So this is one of the researcher, so Black 69. So he mentioned that because our approach gonna be a lot of more into this academic discussion on how we can deal with this power management inside this SoC. Right. So this researcher, I mean, he said that the mean time to failure of aluminum interconnects exponentially decrease as the temperature of a chip increases. right? So if you are using, some part of these aluminum interconnects in your chip, right? So as the temperature increase, the lifetime of the connection will be decreasing. So that means as the temperature increase, you are shortening the life of the IC of the product. So this is something that we don't want it to happen, right? So that's why this is the other driving factor, right, for having this low power SoC in the market. Right, so therefore, cooling down the chip temperature is essential. Then contemporary performance optimized from microprocessor dissipate as much as 5 to 50 watt as using the 100 to 100 megahertz clock rates. So just imagine that this is 102 megahertz, but yeah, do you know, guys, what are these the clock rate that being used in your computer? Any guess? Shah, Q, Yip?
2.4 gigahertz.
Yep, that's right. So just imagine how much power dissipates, right, from the our own laptop. So that's why if I mean, I'm not sure, it's depend on your processor capability, right? But if you are opening something that too much, right, and that needs of heavy processing, for example, this any CAD tools, right, design tools, you open it, and then you're gonna hear the sound of the fan starting to turning on, right? Right, as more processing involved and more heating being released, and then more power will be sent to the fan, to bring out as much heat as possible. So that's why when that guy, the link of the video that I give to you guys, when he talk about why having this M1 processor, so it is a low power consumption, right? And then when low power consumption and it dissipate lower heat, when it dissipate lower heat, so I mean, there is a possibility that Apple doesn't need to include fan inside their MacBook. Right? So when you don't need to include fan, so you have more space, right? More space, and even you can make the laptop thinner and lighter. So those are the things that people that they're looking into, right? So lighter laptop, power but still powerful as the normal laptop. And then the leakage power issue makes this situation worse because the leakage power increase exponentially as the temperature of the chip increase. Right. So as you increase the temperature, and then the leakage power will also increase. We're gonna see what does it mean by leakage power. Right. So leakage power, as a general idea, so it is the power loss, right? That we are not optimizing it, right? So we just lost the power like that. For an example, right? When they want to send the electrical power, right, from the generator to our house, so they're gonna go through a lot of lines, right? So let's say they generate certain power from the generator, and then they send it. So a lot of power gonna be leak throughout the transmission line, throughout the step up, step down transformer, until it comes to our house, right? So might be the one that arrive at our house might be is just 60% from the one that they are transmitting from the generator, right? So there's a power leakage, so you don't want that, right? So because those are all the loss of money, so that's why they try to optimize it so that you decrease as much as possible the leakage power. Right, so in future it is expected that 10 centimeters squared of microprocessor with like 500 megahertz clock frequency consumes about 300 watts. So the cost for cooling such chip is huge. Right, so if we don't do something, right, so this is what happened. So as the microprocessor getting compact, and then can use higher clock frequency, the power consumption will be too much, as and then the cooling cost that you need to have gonna be also increased, which is not intended, because there are a lot of methods, but we are not going to cover it in our class. So there are a lot of methods for cooling, right? So the material, the fin, or the external cooling method that you can use, but these are all involving the costs which are not intended in the SoC design. Right, so consequently, there's a clear advantage to reducing the power consumed in computer system. Of course, I mean, right? So a lot of things that can be done when after you reduce the power, especially for consumer products, right? Okay, so these are the theory that we're gonna be using, right? So this is our base of the theory that we're gonna be using throughout our lecture. So this is the power consumption, right? Power consumption is consists of the P dynamic and the P leak, right? So the power dynamic is the power that being used for the circuit, and then the leakage power is the power that leak right into various places that we don't want it to happen, but it will happen because we have no control of it, but we can reduce it. Right, so these two things, right? P dynamic is P that we are really the one that we are utilizing it, and then the P leak is the leakage, right, that we are not able to control. All right, and then when we expand this formula, we can see so there are a lot of components, right, that contribute to the whole total power that being consumed in an SoC. For an example, right, so you can see all these details of the name. Right, so SA is this switching activity of gate. Of course, the gate gonna switch right from 0 to 1, 1 to 0. So all the switching activity right, will consume power. All right, and then the CL load capacitance. So you know some of the it's depend on the type of the what do you call it, the type of transistor that you're using. Some of the design, they you need to use the capacitance or whatsoever. So the load capacitance, there's a leakage in the capacitance, and you need to continuously pump in the power, and then there's also consume the power. And then of course this is the VDD, the operation voltage. To activate each transistor, you need to supply the voltage. And then the last one is the P leak. So you guys need to know all these components, right? And then the energy is the total power consumption that being used for the SoC. Okay, all right. So here's some more explanation. Okay, yeah, it's gonna be boring. I've told you guys, right? So, but bear with me, right? So we treat the energy consumption E as an objective function to be optimized. So the E is the thing that we want to optimize here, right? So because the energy consumption is so closely related to heat and reliability of chips, so battery lifetime of portable devices, the number of nuclear and gas turbine power actually required. Right, so these are all the theoretical things. So since the power consumption P dynamically change according to the behavior of the software running, right? Because like I said, so the power dynamic, right, is depend. So if you are running, like lower processing application, you don't consume a lot of battery. Right? For example, you just use it for maybe watching a picture, right, from your phone memory. So that's the activity that don't consume a lot of power. But then if you go and play games right on your smartphone, so that's the thing that gonna consume a lot of power, because what there's a graphic involved, sound, right? So a lot of processing involved. So that is meant by dynamic power. So sometimes you use a lot of it, the power, and sometimes you use less of it. So we can see how to optimize, right, the energy consumption. So we can see we have to play with all these component, right? So the SA switching activity, the CL capacitance leakage, capacitance loads, right? The VDD, right? The power supply, the voltage that we supply to these gates, and also the power leakage that comes from the gate itself, right? Okay, so but the thing is that you just you cannot just reduce the whole thing, because if you reduce the whole thing, what gonna happen is that you're going to degrade, right? You're going to degrade means that you're going to lower, right, the computational quality, because it's going to affect the time, the system gonna might not be reliable, because you lower down all the power and also the design flexibility. So the key point here is that the energy regulation SoC design need to consider the trade-off, right? So normally when we talk about computer architecture, computer design, we're going to talk about the trade-offs. So what are the features that we are willing to trade, right, to have the thing? So if you want, for example, if you want to get, a lot of money, you have to trade, right? You cannot sit down and just, moving your feet around, then you are hoping that you're going to become rich soon, right? So there is a trade that you need to make, right? So if you want to make more money, then you need to spend more time on doing something to get money. Right? If you want to get more money, then you need to take some risk. Some risk of losing your money, some risk of losing your friends, some risk of losing might be your family, something like that. And so those are the things, the trade off. Are you willing to trade it off? Right. So in this SoC design, so I mean there are a lot of things that we are looking into, right? So the energy consumption. So if energy is the important matter for the end product, so are you willing to trade off the performance? If you're willing to trade off the performance, how much performance that you are willing to trade off? Right, the computational quality. Computational quality means that the accuracy level, right? Maybe until what decimal point that you want it to be, to be accurate of, right? System reliability, are you going to use the system where the temperature is 100 degree Celsius, or are you going to use the system in the normal normal temperature conditions? So these are the things that you have to look into lah, when you want to optimize the energy management in the SoC. Right, so the goal is minimizing the energy consumption under the constraint of performance, functionality, systemability, or design flexibility. All right, guys. Any questions? There are a lot more to go, right? Bear with me, yeah. But don't worry, we have the recording, so maybe later you guys can watch it again and again to get a better understanding of it. Right, so I think let's take a break. So I think let's take a break, like around 10 minutes break. Then we're going to continue 10 to 11. So we're going to continue at 12:10. Okay, guys?
Okay, Atta.
All right. Okay, guys. Now it's already 12:10. All right. Are you guys there?
Yes, doctor.
Okay. All right. Okay. So let's continue, guys. Okay. So when we talk about power dissipation, right? So when we look into SoC, so there are 2 points of looking at it, right? So the first one is in terms of the location of gates. So imagine this is your processor, right, or your SoC design. So we're gonna have a lot of circuitry, right, on the circuit, but there are some point of the circuit, right, they're going to consume a lot of power. So for an example, maybe a floating processing unit, right? So maybe like this part of processor is gonna do a lot of processing on this floating point. So floating points mean that when there's involving like point number calculation. So if you are using the application, a lot of application or the application that you are using is focusing on floating point processing. So at this particular point of SoC, that is going to be heated up a lot, right? So that's why we can see here they map the power consumption in terms of this what do you call it, location on the chip, right? So and then the second thing, so the power consumption is also related to the program, right? So right, if you are like what I've told before, so if you are running a low power consumption program that doesn't consume too much power, for example just opening an application to view a picture, so that we won't consume too much power. But then all of a sudden, I mean, you open an application that need to process a lot of data, like games, video games, or maybe movie editing. You do some video editing on your phone, so then it's gonna consume a lot of power, right? So that's why even in terms of application, they also have application that going to give you advice on power consumption. I'm not sure if the phone that you guys are using. For an example, I'm using like Vivo phone, right? So whenever there's application that consume a lot of power, they're going to give some notification to me, right? So telling me that okay, these apps consume a lot of power, right? So do you want to consider on turning off this app, something like that, right? So these manufacturer, they are really concerned about power because they want to optimize the battery usage so that the user can feel great about their device, right? Okay, wait now guys, I'm getting a phone call. Sorry guys, you guys remain in here. I need to go in the other room. Right, guys. Okay, I'm back. Sorry for the disruption. Uh, okay, let me present my screen. Okay, guys. All right. So, right. So that's basically it. How the power dissipate, right? So we are talking about the program that we are running on the SoC. So some of the program might consume more power compared to the other program. Right. So there are a lot of techniques that being used to lower down the operating frequency. So we have to look into the compatibility of different voltage standards and then power delay trade-off. So it's involved. We're going to discuss in details after this, right? So this is just a point that we're going to look into. So compatibility of different voltage standards. So this is example on how the static power leakage occurred in this, CMOS design. So giving example, so let's say there are two transistors, right, that sit next to each other. So and then the voltage for VDH is larger than the voltage that being supplied to the neighboring transistor. So what happens when there are differences in the voltage? So there will be a static current flows, right, from this to the input cells of the VDH. So this is the the leakage that we want to get rid of, right? So we cannot just cut off the connection because it has to be connected. Right? So as you can see in the figure 3, right? So uh, there are a lot of approach that being proposed by the researcher. For example, this group of researcher, Sami, they propose, a clustered voltage scaling technique which assume two different voltage available and find the optimal voltage assignment to each cell. So is this one, the approach is more on, you try to group, the transistor. So you try to make sure that the neighboring transistors are having the similar voltage, right? So when you have similar voltage, they are not gonna be the static current leakage, right, from one transistor to another transistor. And there's another technique, but they can propose, right, but back into this, practicality, then we have to see whether it is implementable or not, right? Whether we can implement it in our design or not. And then Johnson et al. So this is another group, right? So they propose a multiple voltage scheduling techniques for reducing the energy consumption of data pass circuit, considering an energy overhead. So schedule, right? So we schedule the voltage, right? So we are not giving, those two voltage at the same time. So we schedule it, right? So that each voltage will be giving at a different time, right? So now we look into power delay trade-off, right? So although lowering the supply voltage is the most effective, right? So when we talk about reducing the power, right? So of course we are reducing the supply voltage, right? But the thing is that when you reduce the supply voltage, what happened? So this will increase, the circuit delay. The speed of the electron traveling is depend on the voltage difference, right? The higher the different of the different voltage, the faster the speed gonna be. But as you lower down the voltage, of course you're going to increase the delay because the signal right now is traveling slower, right? Which determines the maximum clock frequency of a synchronous circuit. So the delay of CMOS circuit can be approximately formulated as 3.1. So this is this one, the formula that we are looking into is the threshold voltage of CMOS transistors used in the circuit. Right. So basically, we have the following three ways, right? Following three ways. So as we can see, this is the delay. So the delay as the voltage reduce, right? So the delay will increase. So this is inversely proportional, right? So as this as this As we lower down, right? So we lower down the voltage, then the delay will keep on increasing, right? So it's inversely proportional. All right. Right, so basically we have the following three ways. So they are in this, when we talk about power delay trade off. So there are three ways, for lowering the operating voltage without sacrificing the performance of the system. So now we are looking into the method lah. So we are talking about, okay, we know that we want to reduce the energy or the power consumption by lowering down the voltage, right? But the problem is that when we lower down the voltage, we're going to increase the delay. Okay, now we will see and we will look into three methods that you can have. Now you can lower down the operating voltage, but not sacrificing the performance of the system. Alright, so the first one is parallelized test, so that the performance does not degrade even in a low voltage operation. We refer this as static voltage scaling. Okay, we're gonna look into example after this. And then the the second one is maximum available supply voltage for gates on critical. Use lower supply voltage for the other gates. So this is multiple voltage assignment. So each path or each connection, we're going to supply different voltage, right? So on the critical path, we're going to give high voltage, and then on the not critical path, we're going to use the lower voltage, right? So that is what we call as multiple voltage assignment. And then the third one is we lower down the clock frequency and operating voltage when the maximum performance is not needed. So this is what we call as dynamic voltage scaling, right? All right. Dynamic is that you can change it, right? At any time. So that means dynamic. So when people say that you need to be dynamic, to work at this company, that means you have to be able, you know, to uh, to adapt very fast, right? Sometimes the environment keep changing, so you have to adapt and follow the whatever happening around you lah. So that's dynamic. Okay, this is example of static voltage scaling. So suppose we have four sequential tasks, right? So this is figure 4a. So we have four sequential tasks. So task 1, task 2, task 3, and task 4. So it's being executed in sequence, right? So the energy consumed is 100 joule, right? So 100 joule to process each four tasks in sequence. But if we execute, right, we execute the task in parallel, right? So at the same time we execute task 1 and task 3, of course the time taken will be longer, but we still serve the same end time, right? So as long as we complete the whole process at T4 is fine. So by using parallel execution on this task, so we can save. You see, the energy saving is 20 from 100 joule to 25 joules, right? So that means we are saving around 75 joules, right? So, but this is only can happen if the task can be executed in parallel, right? But if there is a dependency occur, right? For example, to execute task 3, you need to have something from task 1, right? So you need to have task 1 to be completed. So that's why example showing here that they execute task 1 and task 3. So maybe even let's say for example there's a dependency here, right? So it can wait after task 1 finish, then you execute task 2 and task 4. Still can achieve this energy saving. Right, so although switching activities per unit time may increase up twice, but we can reduce the number of cycles and VDD by half. Right, so as a result, energy consumption can be quarter without performance degradation. So we still have having the same performance, right? Having ending at the same time, but we still save a lot of energy. So this is one technique. So on static voltage scaling too, so a lot of researchers have proposed methods incorporating architecture level voltage scaling. So this group of researchers, Chandra Kasen et al., so propose Hyper LP, which optimize data flow graph generated from a target application program for reducing the power consumption of data pass circuit. So they need to do it on the architecture level. So that means you have to go and look into the circuit, right? So whether the circuit can be run in parallel, to execute the program in parallel, and then you have to incorporate it, do it on the architecture level. Right, so other methods try to transform the target circuit during scheduling. So modules selection, resource binding, minimizing power consumption. So so I think this is being done on the software level, right? So during the scheduling, so how you schedule, and you select all those programs that can be executed in parallel. Of course, if you want to execute something in parallel, your architecture need to support the parallel processing. So that is also come with this the cost. But again, when we talk about trade, right? So what you want, right? In the end, what are the things that you have priority for your product, right? Is it cost or is it power consumption? So it's really depend. Right? So all of the methods mentioned above try to exploit parallelism in the algorithm to shorten critical paths so that lower supply voltage can be used. So I think that's the idea of having custom SoC lah. So when you have custom SoC, so you can choose, you can know what program that you want to run. So based on the program that you run, then you determine whether you need to have parallel or whatsoever. You want to optimize the power for your SoC. So although this is a very attractive approach, parallelization of the computation is very difficult because some computation are inherently sequential. So this is the challenge. So although, for example, you have the architecture, to execute in parallel, but if most of the programs, they are designed to run in sequential, means that they are depending each other. They need to wait for the previous the first instruction to be completed, then they can execute the second instruction, right? So inherently sequential. Right, and then multiple voltage assignment. So this is static voltage scaling. So now we go into the second technique, where we can lower down the voltage without sacrificing our performance. So the second technique is by using a multiple voltage assignment. Alright, if you look into multiple voltage assignment, so most voltage scaling techniques assume that the circuit operates at a single supply voltage. Yeah, of course, the easiest way, you just connect one single supply voltage and you pump out to all the circuitry, right? Although substantial energy saving can be achieved with a single minimum supply voltage, one cannot always take full advantage of available schedule stack to reduce the supply voltage. So, but if you want to have a saving, you cannot reduce, right? If you have only single supply voltage, then you reduce it, of course, it's going to affect, right? So, as we talked earlier, right? The voltage is inversely proportional with the delay. As you reduce the voltage, then the delay will be increasing. So since past delays in the circuit are not uniform, supply voltage of gates on a non-critical path can non-uniform path delays. The critical path delay determine the clock period. Okay, later we're gonna look into example lah. So in this case, non-critical paths used only for part of clock period. Right? I think it's easier if you look into example. All right. Okay, this is example of multiple voltage assignment. Okay, so we have to know which path, right? So this is one path, one path, right? One way of the signal to travel, right, from point A to point B, and then this is another path, right, for the signal to travel. Okay, so based on the the designer, right? So they have to determine which paths that considered as critical path for them and which path is not considered as critical path. Critical path means that they need to ensure that everything goes in time. Yeah, for the signal, for example, the time arrival or whatsoever, right? So that is meant by critical path. So after they have determined the critical path, then they can use, high voltage means that, standard voltage supply for the path, right? But where the path that doesn't, really have, the critical features, so you can use at least lower down the voltage a bit. Right, so instead of supplying the same voltage, for example, 5 here, 5 volt on top here, and second here, 5 volt. So might be 5 volt on top, and then down here, maybe you supply 4 volt, right? 3 volt is depending on the functionality of the circuit, right? At what voltage they need to have for them to operate. That's why if you look into data sheet, right? Normally they're going to give you range, right, for the devices to operate. For example, the high, I mean, for the circuit to read S1, so what are the voltage that they need to receive? For example, 3.3 volt until 5 volt, right? So you can see the range. Right, a bit. Right, so for high signal, right, so the voltage threshold might be 3.3 to 5 volt, right? So for zero, maybe it's 0 to 0.2 volt, right? So as you lower down, so you have to ensure that you still meet this 3.4, something like that, right? So you have still to meet this requirement, lah. Right, so that's why, like, I mean, you cannot just simply, okay, I want to save power, so just lower down the voltage. No, cannot. So you have to make sure that you don't violate, these main rules, the requirement for all of the gates. Okay, all right. So again, there are a lot of, methods, technique that being proposed on this multiple voltage assignment. So USAMI, so this is another group of researcher. They propose a voltage assignment algorithm which finds the optimal voltage assignment to each cell, considering a level shifting cell from different voltages. Right. So I mean, you have to have an algorithm that will find the optimal voltage assignment to each cell. Right, so it's going to look into this is not cell, right? So it's going to look into every cell, and then considering level shifting between voltage, right? So like I think this the example that I've shown before, this one, and look what are the voltage. So you can have a multiple different voltage assignment to reduce the current leakage. All right, so and then the algorithm performs backward graph. Okay, this is another one. So I mean they have to trace each line. So go and trace each line from from of given at least from outputs toward the primary input. So it go backwards, right? From the output it goes to the inputs, and then try to find which one is the critical path and which one is not the critical path. Right, so if the timing constraint is still met after the replacement, then cell is replaced. So means that replaced with the lower VDD cell, right? So the main idea is that you whatever you want to do, as long as you don't violate the timing constraint, then that's okay. But if you violate the timing constraint, then of course your design gonna be wrong, lah. So the process will be repeated until all cells are validated. So from their experiments, so they say that the energy consumption can be reduced by 20% using voltages from 5 volt to 3 volt. This is okay, yeah, not bad. At least they can reduce 20%, which is I feel still contribute a lot to the final design. Alright, so another about things about multiple voltage design. So the idea can be extended to multiple voltage data path scheduling technique in high level synthesis. Okay, so this is another method, right? So another method. Okay, let's look into example. Right, so this is the standard one, right? So the standard one, so if you execute, right? So at each stage, so there's a adder and also multiplier what they call it, program, right? To be run, right? So add a voltage of 1.7 volt, so you can achieve, smaller area, and then smaller delay, means that you can execute it faster. But the problem is that the energy consumption is high, right? So you can see adder at 1.7 volt, so energy consumption is 2 joule, and then multiplier at 1.7 volt, the energy consumption is 4 joule. All right, so this is one way of running it, right? So in the end, the area consumption is 3, and then the delay is 3, which is low, and then but the energy is the highest. But it's depend, right? It's really depend, on how you sort it, right? So instead of executing this, in this way, so you can break it out, right? So you can break it out. For an example, so you can execute the this adder process first by using 1.7 volt, but then the another multiplier operation here, and then the adder operation here, you can run it at 1.2 volt at lower voltage, but of course the delay will be increased a bit. But in this case, if you know how to sort it very well, right, so you're gonna still have the same delay 3, but with lower energy consumption. All right, so this is by using what they call it as, uh, data path scheduling technique. So how you schedule, all the operation in your data path. So, and if you can schedule it, of course, when if you want to schedule, your architecture need to support it, right? So you need to support, multiple execution at the same time, right? So here, then you can achieve the same goal, which is delay 3, but with lower energy consumption. All right, so the area required, this is all the explanation about it, so you guys can go and try to read it later. Okay, and then this is the third one lah. So this is regarding again, we are still in the same discussion, but we try to reduce the voltage, but we don't want to sacrifice the performance. And then the third method, which is the last method, is dynamic voltage scaling, right? Right, so it's more aggressive approach. We call it is dynamic voltage scaling. So since the computational load is not constant during execution of given task, we can control computational power according to the computational load. So I think it's easy if you look into graph now. Okay, if you execute whatever operation, by using the same voltage, right? So this is the power that you consume, right? 40 joule. Of course, the time is better, right? You save 5 seconds, right? So you finish the processing ahead before the time constraint ends. Or what you can do is that, you can execute, part of the application which need, high voltage at the time by supplying high voltage, and then when the application doesn't need any powerful processing, then you can lower down the voltage, right? But whatsoever, you have to meet the timing constraint. So this is the what I call it, the dead end so you cannot cross this. Once you cross this, then there's nothing to be talked about lah. So we now we gonna work within this constraint, right? So by having this method, then we can reduce to 32.5 joule, right? Or we can find, optimize voltage, which is 4, which will not compensate, or sacrifice any performance. So we just execute the whole application at 4 volt, and we consume only 25 joule of energy. So this is what they call as dynamic voltage scaling, right? Okay, so this is the explanation. Right, so this one, Ishihara and Yasura prove that the following theorem: if the processor uses a voltage V ideal and completes a given task just at a timing constraint, T constraint, The V ideal is the ideal voltage which minimize energy consumption for the task lah. So this one lah, V ideal. So we need to make sure that this V ideal mean all, so whatever lower voltage that we can use as long as we meet the time constraint. So that's what being proposed by Isyara and Yasura lah. So there's a figure, this one the figure let's be showing the example. Okay, alright. Wait okay, there's some more. Okay, wait, almost done guys. Okay, stay with me. Okay, so there are three major sources as follow. The first one occurs when a system is not tightly designed for a given processor. In other words, there's a room for design change or improvements, such as introducing more tasks, replacing certain tasks with their version up using lower performance processor, and so on. So these are the another thing when we talk about how we can reduce the power consumption. And then the second source comes from a nature of fixed priority scheduling, the ideal intervals in here in the fixed priority scheduling, because the priorities statistically assigned to the task are not always optimal for the task. So these are the three major sources. This is just for the sake of discussion. You guys can go and read it. All right, so the last one we want to talk about power reliability trade-off. So since the voltage scaling techniques reduce voltage margins, it is impossible to discuss about low power design techniques without considering reliability issue. Right, so when you lower down the voltage, like I said before, right? So we have to make sure that it's still reliable. Means that it won't disturb the functionality of the SoC lah. So we want to save power. We provide low voltage, but then it's not function as what we want. So we don't want it to happen. So that is a trade-off that we not the power reliability trade-off that we have to look into, right? Okay, so there are three measures, right? So voltage margin. So the first one is process margin. This ensure that performance uncertainties resulting from manufacturing variation do not prevent slower devices from completing computation within a clock period. Okay, so this is, so we have to ensure that nothing that will slow down and then disturbing the completing the computation within a clock period, the timing constraint. Ambient margins ensure correct operational at worst case temperature. So we have to ensure that if our design can work in the desired temperature, right? So if you lower down the voltage, is it going to work at a cold place or very hot place, right? So it's depend. Noise margin, so the noise of the label. So if you lower down, so does it will create noise, and in the end will cross coupling or disturb your logic signals. All right, so I think these are the things that you can read about. So and then this is one of the technique lah. So they monitor, right? So as you lower down, and then they monitor the error rates, right? So how much error that they have if they lower down the voltage. So the simulation results show that energy consumption can be reduced by 56% over conventional interconnect with more robustness to large variations, actual workload, noise, and technology quality, right? So I mean, like I know you can have a lot of apply the method, right? And then having the energy consumption reduced by almost half, right, from the initial. Okay, all right. So we have reached at the final slide for today. All right, guys. So this one is for you guys, right? So commercial products, you guys have to look into. So there are a lot of commercial products that being used for power management to support dynamic voltage scaling. Right. So I want each of you guys to go and look into all of this technology by AMD, via technologies, Transmeta, TI, ARM, right? And then prepare a slide for it, then present in our next class. Right, so we're going to discuss about the commercial program. Then after that, we're going to continue with our discussion. All right. Any question, guys?